And now our second theorem is a partial converse to the previous theorem. And here we have again a topological space X and a metric space Y. And here we are assuming that X is a compact space and Y is totally bounded under the metric D. And the statement says that if F is a set which is equicontinuous under the metric D for Y, then F is totally bounded under the uniform metric rho bar. And this is a partial converse, as I said, partial converse to theorem 4.1, because there we did not assume anything on X and Y, and total boundedness implied equicontinuity, but here we have to put some extra conditions on the spaces X and Y. So let us look at the proof of this theorem. Now for the proof, we assume that F is equicontinuous under D, and we have to show that given any epsilon greater than 0, F can be covered by finitely many open epsilon balls in the rho bar metric. And we assume, as always, that epsilon is less than 1 as well, and that simplifies our analysis for using the bounded metric as before. And so now let delta be epsilon by 3 again, and by equicontinuity for each point A in X, there exists a neighborhood UA of A such that if X belongs to, so for all X in UA and for all F in F, we have that the distance between Fx and Fa is less than delta, and this is by the equicontinuous property of the family functions F. So now cover X by finitely many such UAs, so say UA1, UA2, UA capital N, and let UK denote the set AK. So this is by compactness of X. So we have assumed that X is a compact space, and because all these neighborhoods form an open cover, there is a finite cover of X by UAs. And now let us consider the set. Let us consider the finite cover of Y by open delta balls in the D metric, of Y. This is by the total boundedness, of Y, and therefore, so there exist, let's call them V1, V2, V capital M, such that so these are VI's are open and cover Y, and with the diameter of VK is less than delta for all K in the set 1, 2 up to capital M. So this is possible by the total boundedness property of Y. And now we consider the finite sets. So we have the sets U, I from 1 to N, and Vk, K from 1 to capital M. And now we consider the set J of all functions from the finite set 1, 2 up to N to 1, 2 up to M. So the set J is finite. J is finite, being the set of all functions between two finite spaces, and we will use this set of all functions. We will use J to label functions in F. So our labeling scheme is the following. So now, given any such function, if there is a function f in our set F such that f of ai belongs to v of alpha I, so the image of ai belongs to one of these v's because it covers y, and there will be some index to which it belongs, and that is alpha I. Here we are asking it to belong to alpha I for each I. So for each I in 1 to up to n, then we choose one such function and label it as f alpha, and we claim that this, so first of all the collection f alpha is labeled by a subset j prime of j, and so it is a finite set, and we claim that f can be covered by epsilon balls with center f alpha for alpha in J, and therefore since J is a finite set, we have that. So of course these are in the row bar metric, so then f will be totally bounded under the row bar metric. So let us show this. So for this, let f be an arbitrary element of our set F, and for each I in this set 1 to up to capital N, choose a number alpha I which belongs to the finite set 1 to up to capital M, such that f of ai belongs to v of alpha I. This is possible because the v's on this index set 1 to up to m cover all of y. So then the function alpha belongs to our index set j prime. Alpha is a function from the set 1 to up to n to 1 to up to m. It is well defined, and because there exists a function for each such alpha, then there exists an f alpha corresponding. So this f alpha belongs to f, of course, corresponding to this given alpha. So this is the particular alpha that we will choose. Now we will show that for any x in the domain x, we have that the distance between f alpha x and fx is less than epsilon. So for this, note that given any x in x, so there exists an I in 1 to up to n such that x belongs to ui, and remember that this was uai for some point ai in x, and now we have that the distance between f alpha x and fx is bounded above by the triangle inequality again. So first we plug in f alpha ai, then we add it to f alpha ai fai, and then we use fai and f of x. So again, let us choose some notation 1, 2 and 3. So then we have that 1 and 3 are less than delta by the choice of I. So x belongs to ui, and our neighborhoods ui were precisely working for all the functions in the set f. So both for f alpha and f, we have that these two are less than delta, and 2 is less than delta. This is less than delta by the fact that both fai and f alpha ai belong to v alpha I, and the diameter with the metric d of v alpha I is less than delta. So therefore this implies that the distance between f alpha x and fx, distance between f alpha x and fx is less than 3 delta, which is equal to epsilon. So this shows that f is totally bounded under the rho bar metric, since rho bar of f alpha is equal to the supremum of d bar f alpha x fx, x in x, and this is less than epsilon, which is less than 1, if and only if the supremum of d f alpha x fx, x in x, is less than epsilon, and this is if and only if the distance between fx and f alpha x is less than epsilon for all x in x. And this is what we have shown here. This is for any x in x, so the supremum also is bounded above by delta. And this completes the proof of the theorem.